escuchan por acá? Ok. Pero... Buenas tardes a todos. Sean bienvenidos al ciclo ICAT Aurum, ciclo conmemorativo del 50 aniversario del ICAT. Como parte de la conmemoración del 50 aniversario, este ciclo de conferencias magistrales busca seguir cultivando el conocimiento y las colaboraciones para el desarrollo de la ciencia, enseñanza y la tecnología. Les invitamos a participar en las actividades programadas durante todo el año dedicadas a esta celebración. Bien, en esta ocasión contamos con la presencia y el honor del profesor Derryck Reid de la Universidad de Heriot-Watt de Edimburgo, Escocia. Para comenzar, voy a dar la semblanza del profesor Reid. Derryck Reid obtuvo su grado como maestro en las artes en ciencias naturales en la Universidad de Cambridge en 1991 y su doctorado en la Universidad de St. Andrews en Escocia en 1994, realizando su tesis en osciladores paramétricos ópticos de femtosegundos. Posteriormente, en 2001, se integra a la Universidad de Heriot-Watt, donde forma su grupo e inicia su carrera como líder y fundador del grupo de óptica ultrarrápida. Posteriormente, en 2005, muy joven, lo hacen profesor en la Universidad de Heriot-Watt. El profesor Reid pertenece es miembro de diferentes institutos y asociaciones, entre los cuales, son muchos, voy a destacar. Pertenece él es fellow en el Institute of Physics del Instituto de Ingeniería y Tecnología. Es fellow en el Royal Society de Edimburgo y en el fellow at the Higher Education Academy, fellow of the Optical Society of America. Su historial en su carrera, bueno, pues de 2015 a 2018 fue, lo más destacado, fue director del Instituto de Fotónica y Ciencias Cuánticas de la Universidad de Heriot-Watt. En 2013 fue director del EPSRC, del Centro para Entrenamiento Doctoral y Fotónica Aplicada. De 2012 a 2018 fue director del EPSRC, del Industrial Doctorate Center in Optics and Photonics Technologies. Es editor invitado en diferentes revistas de prestigio internacional, miembro de diferentes consejos editoriales, invitado de honor en diferentes comités e instituciones. Es amplio su trayectoria. Su carrera en el campo de la fotónica cuenta con una brillante trayectoria de 30 años, motivada por las aplicaciones de las fuentes de pulsos ultracortos que incluyen metrología óptica, peines ópticos y síntesis coherente, microscopía no lineal, desarrollo de fuentes de pulsos láser de femtosegundos novedosos y osciladores paramétricos, procesamiento de materiales con pulsos láser de femtosegundos. Desde hace varios años, Derryck es ampliamente reconocido a nivel mundial por sus importantes aportaciones en el campo de la óptica ultrarrápida, por mencionar algunas. la invención de la caracterización de pulsos de femtosegundos utilizando autocorrelación de dos fotones con diodos semiconductores. Y la demostración por primera vez de la generación de peines ópticos de femtosegundos basados en oscilación paramétrica óptica. Esto es entre algunas de sus aportaciones más relevantes. De acuerdo con el Google Scholar, cuenta con más de 400 artículos, un índice H de 39 y tiene alrededor de 5.600 citas. A lo largo de su carrera ha logrado el financiamiento a través de proyectos por alrededor de 28 millones de libras. Ha sido, como mencioné, director. Mantiene vínculos importantes con el sector industrial en Reino Unido. Y desde hace aproximadamente 22 años, Derryck tiene una estrecha relación con el ICAT a través de la colaboración con diversos académicos. Haciendo un poco de historia, bueno, la relación con el CECADET, ahora ICAT, inicia a través de un ex estudiante de Roberto Ortega, Pablo Loza, quien es conocido aquí ampliamente. Pablo realizaba sus estudios de doctorado en St. Andrews y fue que coincidió con Derryck alrededor del año de 1998. Posteriormente, Pablo presenta a Derryck con Roberto Ortega, y en ese entonces Roberto Ortega iniciaba su investigación en la óptica ultrarrápida. Entonces Derryck decide invitarlo a realizar una estancia junto con Carlos Román en su grupo en Heriot-Watt. El trabajo de esta colaboración derivó en una publicación. Por las mismas fechas, en el año de 1999, también a través de Pablo Loza, quien realizaba en aquel entonces una visita al CICES en Ensenada, donde yo me encontraba realizando mi doctorado, tuve la oportunidad de conocer a Derryck, que inmediatamente propuso algunas ideas de lo que yo estaba, en relación a lo que yo estaba haciendo, que coincidía con lo que él tenía. Y a través de esta colaboración fue que pude publicar mi primer artículo en óptica ultrarrápida. Posteriormente, cuando terminé mi doctorado de 2002 a 2004, me da la oportunidad de realizar una estancia postdoctoral en su grupo. Bueno, actualmente continúa la colaboración con Derryck a través de trabajo en conjunto con el grupo de óptica no lineal y el de instrumentación óptica, que ha derivado en publicaciones. Ha impartido pláticas y ha impartido un taller durante la realización de una escuela de verano, y ha ofrecido la oportunidad a nuestros estudiantes que hemos graduado a realizar estancias en su laboratorio, visitas cortas y a realizar tesis de doctorado, así como estancias postdoctorales. Bueno, además de ser un gran investigador, reconocido ampliamente a nivel mundial, quiero destacar que Derryck es una gran persona que mantiene sus rasgos de generosidad y humildad desde que lo conozco, cuando era él también estudiante de doctorado, y siempre, a pesar de su apretada agenda, se da tiempo para aceptar todas nuestras invitaciones y contribuir de una forma u otra al ICAT, en esta ocasión con esta interesante plática titulada Frequency Comb Development for the Extremely Large Telescope, como parte de los eventos conmemorativos de los 50 años del ICAT. Bueno, pues le damos las gracias al profesor Reid por aceptar nuestra invitación. Y bueno, antes de iniciar esta conferencia, permítanme invitarlos a seguirnos por redes sociales como @ICAT oficial y por nuestro canal de YouTube, que encontrarán como ICAT oficial, donde esperamos sus preguntas y comentarios al término de la presentación del profesor Reid. Muchas gracias. Iniciamos.
So, good afternoon. I'm Derryck Reid from Heriot-Watt University, and I'd like to begin by thanking the organisers, Jesus Garduno and also Rodolfo, for the kind invitation to speak at this 50th anniversary celebration for ICAT. So my talk today is going to be on the development of lasers to calibrate the spectrographs that are part of the extremely large telescope, the world's largest telescope, planned for completion in Chile in 2028. That will be first light. And so I want to tell you a bit about our involvement in that project, about the technology of laser frequency combs. But I think to begin with, let me tell you a bit more about where I am at Heriot-Watt University. So Heriot-Watt is a university in Edinburgh in Scotland. So here's the UK, Scotland's the top half, and Edinburgh is located just in here, nearby the Firth of Forth, this river here. And Heriot-Watt takes its name from the famous engineer, James Watt, who contributed to making the steam engine much more efficient, and also from George Heriot, financier to James the First of England. So that's where I am, and I also wanted to make the connection with Mexico. So back in I think late 1999, early 2000, I first met Professor Roberto Ortega Martinez, who at that time was, I think, running and certainly working at the Laboratory for Applied Optics in UNAM. And I believe this went on to become C Cadet, which has gone on to become ICAT now. So we worked together in, he came over to Heriot-Watt University and also to University of St Andrews, where I was just finishing as a fellow there, and was transitioning into my move to Heriot-Watt University in early 2001. So Roberto visited us in both places, and he did some work with my group on developing new methods for characterizing femtosecond laser pulses. And we published a paper together in 2001 in the Review of Scientific Instruments, which was about developing a new rapid technique for fast, complete pulse measurements. That's amplitude and phase. So fond memories of Roberto and his time working in the labs in St Andrews and at Heriot-Watt. This is Roberto in his own lab, I believe, in UNAM. So that's the connection with Mexico, and I visited, I think, on at least 3 occasions, maybe even 4 occasions now. I visited the group at UNAM to do either work in the lab or to take part in conferences or to give seminars. So it's a pleasure again to be able to contribute today. So on to the main subject of the talk. This is the extremely large telescope here. It's an animation depicting how it will look when it's finally completed. So this is in the Atacama Desert in Chile, and the telescope itself is a 39-meter diameter mirror that you can see here. It makes it the largest telescope in the world by a long way, and that light collecting ability that you get from having such a big mirror is a really vital part of why you can do new things with the extremely large telescope. So in terms of the science cases that this telescope will enable, they cover things like exoplanet detection and really more than just detection, actually exploration in terms of their spectroscopy. I'll say a bit more about that in a moment. Star and planet formation, stellar physics, chemistry, and what's called astroarchaeology, looking back in time in the universe, the evolution of galaxies, and also some really fundamental physics, such as if you can measure things like the rate of change of the expansion of the universe, then you can infer from that any small changes in things like what are commonly considered fundamental constants, like the fine structure constant. So some really exciting opportunities. But let's begin by looking at the one regarding exoplanets, which is going to be a significant part of what people use the E-ELT for. So an exoplanet is a planet orbiting some distant star, and as the planet orbits the star also orbits the common center of mass of the planet-star system, meaning that viewed from the Earth, the star moves towards and away from us, causing the absorption lines in the that we observe on Earth in the star's spectrum. Those absorption lines, which have a characteristic pattern because they come from, for example, hydrogen, they shift. And as the star moves towards us, they're blue shifted. As the star moves away from us, they are red shifted. And so looking at the pattern of those Doppler shifts allows us to understand the velocity of the star. We get the orbital period of the planet. We get the light curve, which is a plot of the star's motion as a function of time. And from that, you can infer things such as the mass of the planet. But further than that, there's a really interesting opportunity presented by the massive light collecting ability of the extremely large telescope, which is that the light from the star can be used to back illuminate the planet's atmosphere and therefore conduct transmission spectroscopy through the atmosphere in the visible to the near infrared region. And by doing that, one can look for absorption signatures of life, which are expected to be seen for oxygen, for water, for methane, and for carbon dioxide. And if you can see those signatures, those atmospheric absorption signatures, then you can infer the presence of these molecules and perhaps find a planet that is capable or does support life. And finally, there's opportunities in cosmology, because the more light you can collect, the fainter the objects you can look at, meaning the further back in time you can go. You can look at light that has traveled from deeper in the universe, and that corresponds to earlier in time. So you can effectively look further back in time with this big mirror that exists on the E-ELT. And by using spectroscopy to measure exquisitely small changes in the positions of emission and absorption lines from stars, and doing that over a period not just of days or weeks, but actually over decades, then you can look for systematic changes in the rate of change of the expansion of the universe. And from that, you can infer changes in fundamental constants. So these are really exciting things that are all enabled with spectroscopy on the telescope. And so where the laser side of things comes in here is that the spectrograph on the telescope has got to have a very high resolution, and it also therefore needs to be calibrated very precisely in an absolute sense. And what I mean by that is that the pixels on the spectrograph have to be mapped into wavelength, and to do that we can use lasers. So just to give you a sense of the kind of requirements here and precision requirements in terms of wavelength, for some applications for exoplanets, the precision is about 50 meters per second, and we can understand what that is in terms of a fractional change of wavelength or of optical frequency simply by dividing by the speed of light. So 50 divided by 3 times 10 to the 8, so of order 10 to the minus 7 calibration precision. Now that sounds demanding. It's a relatively modest requirement, in fact, when you compare it with the requirements for doing some of the more demanding studies, which are looking at very tiny changes in the position of absorption lines, changes that are in fact much less than 1 pixel on the detector array. And these changes, they require the spectrograph to be able to maintain a wavelength precision of much less than 1 meter per second. So with a goal of 1 centimeter per second. So that takes you down to 10 to the minus 11 or 10 to the minus 10 precision. And that's where really laser frequency combs, which are the best frequency, I suppose, frequency references that we have to date, that's where they come in. So within the E-ELT, the expectation is that there are a number of separate spectrographs. So light comes in from the focus of the instrument, from the telescope, is fed on fibers into these, 4 different spectrographs, from the blue through to the near infrared. And then within each of these spectrographs, there are a number of cameras, because each spectrograph covers quite a wide range, and that light has to be split up onto several cameras. So that's the idea here. And this is done using chromatic dispersion optics. So each spectrograph must be calibrated, and so a calibration unit is needed. And what this comprises of is a white light source that then passes into and through a number of Fabry-Perot etalons that imprint a mode structure onto that white light, broadband white light spectrum. And that is available perpetually for the telescope to use as a reference. But this white light source and these etalons, they have wavelength dependence, and so they must be calibrated. And so the model being used in the E-ELT is to pre-calibrate this broadband light source using a laser frequency comb, which I'm going to go on to explain what that is in a moment. But essentially the requirement is that this calibration unit must operate from the deep blue through to the near infrared at 2.4 microns. It's got to provide one calibration line every 2 or 3 pixels on the spectrograph. It's got to have an accuracy as good as 10 centimeters per second and a precision as good as 1 centimeter per second. It's got to be turnkey, and it's got to maintain that calibration essentially indefinitely. This is expected to have to run for 20 plus years in order to conduct some of the measurements that are required. So let's now talk about the lasers in more detail. So here is a representation of a continuous wave laser producing just a single wavelength of light, and you can see the constant output it produces. Now, if we allow this laser to resonate on 2 different cavity modes, so it contains now 2 frequencies, we get a beating effect. Now we've added a 3rd frequency here. This beating effect leads to the generation of optical pulses. So here we see an example with 4 different wavelengths added, and we're going to see another one added soon, 5. And as we add more and more wavelengths, and we do that in a way that these wavelengths, in terms of their frequencies, are regularly spaced, we end up creating very short pulses in time from this laser. And this essentially is how a mode-locked laser works, a femtosecond laser. So we develop femtosecond lasers for astronomy that don't just produce 10 of these equally spaced wavelengths, equally spaced frequencies. They produce tens or hundreds of thousands of these modes simultaneously. And that's known as a frequency comb because of the way in which these individual laser cavity modes resemble the teeth of a comb. Now, this allows us to use the output of one of these lasers as effectively like a ruler. Imagine now that these are the marks on a ruler in millimeters or centimeters. You can use a ruler to measure distance very precisely in a standardized way, and in the same way you can use a laser frequency comb to measure frequency and calibrate a spectrograph in a very standard way. So to do this, one has to take a laser and organize it so that these comb teeth are sufficiently widely spaced that they can be resolved by the astronomical spectrograph. That means typically they've got to have spacings in the tens of gigahertz range. But once you organize that, it means that you can take one of these lasers to a telescope, such as the E-ELT or these are all telescopes here, HARPS North, SALT, or these are the instruments rather on the telescopes. And you can use this as a calibrator. So I'm going to speak in a few moments' time about a campaign where we took a laser frequency comb to the SALT telescope in South Africa, and we calibrated from 500 nanometers to about 900 nanometers from the green to the near infrared using a single frequency comb, and that filled the extent of the spectrograph there. As you can see, to do that on the E-ELT, this dashed line represents the wavelength coverage of the telescope. It's vast, and so it's a big challenge to create a laser frequency comb that addresses this full range, operating range of the spectrograph. And in fact, historically, any of the demonstrations of laser frequency combs on actual telescopes have always had to compromise by only covering a portion of the total operating range of the spectrograph, except for our demonstration on SALT. So to say a bit more about that demonstration on SALT, here's a SALT telescope. It's a 10-meter telescope. It's based in Sutherland, which is in South Africa. It's about a 7-hour drive from Cape Town. And SALT is a very accessible telescope. One can actually go inside, one can look at the mirror, and that's what this is. This is the primary mirror. It comprises about 110 of these hexagonal mirrors all put together, giving a total diameter of 10 meters. This is the view from the top on a day that you can't expect to do any observing because it was a pretty wet day on this day. Here's a telescope, and what we did, we looked at making measurements using on one camera on the high resolution spectrograph, high res, or HRS, I think we call it. And that red arm covers from 550 to 890. It's really from green to red. And what you see on the spectrograph, this is a false color image, but what you see in the spectrograph are these multiple orders. It comes from a Nichelle grating inside the spectrograph, and that leads to these multiple orders here. So I'm going to take you through this. You can see if we zoom in, we can see already some comb modes here. So these broad bands, continuous bands, that's what we see in the spectrograph when we introduce our laser frequency comb. And so we can scan around a bit and we can have a look at these. So there's the comb modes, really well resolved in the red region, about 890. We can pan down and we can see those comb modes in other parts of the spectrum here in the green. And again, very well resolved. So these big broad bands, those are the laser frequency comb. That's the laser frequency comb output. But riding on top of those is actually a separate measurement, because this spectrograph has two inputs, which are arranged to give you basically two independent spectra. And the other spectrum measured here comes from a thorium-argon lamp. That's the classic calibration light source that was used before laser frequency combs. And you can see that it takes the form of a number of emission lines, which can vary dramatically in their intensity. Some are really bright, so bright they saturate. Some are really dull, hard to see. Some of them are very sparsely spaced, and you only get maybe 3 or 4 emission lines on one order of the spectrograph. So these are fundamental difficulties in using these emission lamps as calibrators, and you see that the laser frequency comb just gives a much denser and richer calibration axis for the spectrograph. So here is an example of the laser frequency comb that we took to South Africa. We built it on a 1 meter by 1 meter breadboard. It's a Thai sapphire based frequency comb. Here's a green pump laser, here's a Thai sapphire laser, and then other components to create the frequency comb. I'll go into detail in a moment or two. But essentially, we took the output of this laser frequency comb, we coupled it into fiber, and we introduced it along with light from the thorium-argon lamp into a fiber that led to the spectrograph. The spectrograph itself looks like this. There's an entrance slit, light comes in, it's collimated from a primary mirror onto a Nichelle grating. it's returned, and then after it's returned to not far from the slit, that light is broken into two channels, red and blue. We looked at the red channel here, and that light is cross-dispersed using a volume Bragg grating to produce a two-dimensional image on the surface of the camera, as you saw. So here's the actual spectrograph. It lives inside this vacuum chamber, and there's an astronomer at full scale, just to give you an idea. And you can actually see the cameras here. There's a red camera, and there's a blue camera. So you can use the laser frequency comb to calibrate spectrograph and to correct for systematic errors in the spectrograph. So here's just two of those comb lines measured on the spectrograph, and you can fit to them. So the individual pixel by pixel measurements are the red circles. You can do a fit, which allows you to work out the full width half maximum of the instrument, and this is the instrument response function. So showing a resolution of about 4 gigahertz, because these comb lines are, for the purposes of the spectrograph, these comb lines are infinitesimally narrow. You can carry out that measurement across all the different mode orders of the spectrograph, and by doing that you can work out the resolving power. You can also, for a given shell grating order, you can do a fit that recovers what's called the wavelength solution, the mapping of wavelength to pixel on the spectrograph. And we did that on SALT, and we're able to improve by a factor of 2 the wavelength solution, the precision of that. We could also carry out a measurement of starlight, so what's called an on-sky measurement, where we looked at light from this photometric star, LTT 7379. It exhibits a feature known as the H-alpha line, and we were able to measure that directly and calibrate its full width half maximum using simply the comb calibration axis here. And in fact, that gives us a much more precise measurement than we were able to get using an axis calibrated from the thorium-argon lamp. So let's now look at the overall architecture of our laser frequency comb. Now, this is the proposed architecture for the E-ELT comb, and similar to SALT, it's going to be based on a 1 gigahertz Ti sapphire laser. So that has a native mode spacing of 1 gigahertz, but as we've seen, really we need to get to mode spacings in the 10 or tens of gigahertz range, into the 15, 20, 25 gigahertz to be useful, so we can resolve them, because as we saw just here, the resolution of a typical spectrograph is only about 4 gigahertz, so we need to have a mode spacing significantly wider than that to be useful. So we've got the Ti sapphire here, we've got a fiber, nonlinear fiber, that expands its spectrum to cover the visible to the near infrared here. Part of that is used for locking the comb characteristics of the Ti sapphire laser. Another part is taken and used to pump a femtosecond optical parametric oscillator that really serves as a wavelength doubler to take light at 800 nanometers from the laser and create pulses at 1600 nanometers from the OPO. Now, these pulses themselves can also be used for supercontinuum generation, and they are introduced into another nonlinear fiber that covers now from 1 micron to 2.2 microns wavelength. And these outputs from these two fibers can then be used to, filtered using fabry-peroethalons to get the desired mode spacing, and they can be shaped spectrally using spatial light modulators and then introduced into a Fourier-transform spectrometer for final measurement prior to the astrocomb. So let's look at each of these as modules. So here's firstly the Ti sapphire itself. There are two parameters that must be stabilized in order to control a frequency comb. One is the mode spacing, so the gap between modes, and that's effectively the pulse repetition frequency. So that can be stabilized using an intracavity piezo driving one of the mirrors in the laser cavity. That's repetition rate control. The other is the offset of the set of comb modes. So they can be evenly spaced, but their relative position to 0 Hertz can change, and controlling a parameter called the carrier envelope offset frequency allows us to stabilize the comb fully. And that's done using some a nonlinear interferometer known as an F22f interferometer. So the details are beyond what I can talk about here, but this is what it looks like. So we've in the SALT system, we didn't stabilize FCEO, but we monitored it and saw that it was a very slow drift, but we did stabilize the rep rate. That's to say the mode spacing. So the main component of this system here is this nonlinear fiber, a photonic crystal fiber, and it allows us to generate light from the green through to the red as shown here, and here's the actual spectrum that we produce. So this is one of our primary inputs into the Fabry-Perot filters. So let's talk now a bit about those Fabry-Perot filters. There are a number of these planned in the E-ELT, but let's just consider one of them, perhaps this one here acting in the visible in the red. The modes from the laser are represented in this diagram as grey lines, and the modes that are transmitted by the Fabry-Perot are represented in black. And so you can see that the idea is to line up the peaks of the Fabry-Perot transmission modes with a subset of comb modes from the Ti-Sapphire laser, from the supercontinuum. And if you do that correctly, they all line up nicely. If you don't do that correctly, then you get a mismatch in the location of the Fabry-Perot transmission relative to a comb mode. So in order to ensure that you get this proper filtering over a wide bandwidth, we have to use Fabry-Perots with a net round trip group delay dispersion that is very close to 0. We do that by using a pair of complementary mirrors that are equal but opposite group delay dispersions. And so these are the mirrors that we use, shown in green and blue. And then the round trip dispersion in a Fabry-Perot echelon made with these mirrors is very, very flat, and that allows us to ensure this very precise mode filtering right across the whole bandwidth of the supercontinuum from, in our case, 550 to 890 nanometers. So one of the challenges here then is that having set up a Fabry-Perot echelon, so it's shown here, the Ti-Sapphire generates a supercontinuum that comes into this plane Fabry-Perot echelon, and that echelon is then locked by a Didder locking technique that maintains the transmission at the peak of its value. We still have some uncertainties because we can either find that we lock to this set of comb modes shown in blue, or we maybe lock the transmission of the Fabry-Perot cavity to a different set of comb modes shown in red. So the approach we've taken to understanding this is to build a Fourier-transform spectrometer shown here. It's a folded Michelson design, but this allows us to measure, essentially as we scan the path lengths of that Michelson, we measure interferograms along with a calibration interferogram from a CW laser. So these are the interferograms from the frequency comb up the top here and CW laser down the bottom. It gives us an interferogram that we can calibrate and then Fourier transform to get the spectrum of the light from the laser frequency comb. And if we zoom in now, we can see the individual comb modes. Now, what we were able to show was that with this instrument, as we relocked the Fabry-Perot at a different set of comb modes, we were able to see that visually in the spectrum from the Fourier-transform spectrometer. So we could lock on, say, these red modes here, or we could lock on the black modes, and these are experimental results showing the different subsets that we could lock to. Right, let's talk now about how we get into the infrared, and we do that using a femtosecond optical parametric oscillator that uses a nonlinear crystal to frequency down convert light from the 800 nanometer wavelength in Thai sapphire to 1600 nanometers from the OPO. So this runs at a wavelength, center wavelength of 1600 nanometers, but with a bandwidth of between 1 and 200 nanometers. So essentially, each of those modes in the pump laser frequency comb is down converted into a pair of infrared idler and signal modes. So we build this cavity, this OPO, using a crystal of periodically poled KTP, potassium titanyl phosphate. When the OPO is running, we see this lovely green light, which is some frequency mixing between the pump and the intracavity light in the OPO. And as I said, we get of order 1 to 200 nanometers bandwidth in the near infrared. And critically, we can then take the output from the OPO and we can feed it into a nonlinear fiber to get further supercontinuum generation in the near infrared. And that's what we do here. Here's the output from a highly nonlinear fiber pumped by the OPO pulses, and showing that we can get from 1 micron to 2.2 microns. And here you can even see some spectroscopy of water vapor happening due to the absorption at 1.8 microns. So putting all this together gives us a way of covering from 500 to over 2000 nanometers from the astrocomb. Now, I've already spoken about how we can do the filtering in the visible. Let's look now at the mode filtering in the near infrared. So here we take our OPO and we take the output, we put it into a nonlinear fiber, and that output from the nonlinear fiber then enters a plane Fabry-Perot echelon. Now, this allows us then to again do the mode filtering from 1 gigahertz to maybe 10 or 15 gigahertz as is required for the astronomical spectrograph to be able to resolve those comb modes. And as before, we measure the filtered comb mode using a Fourier-transform spectrometer. So here's the output from the Fourier-transform spectrometer. Number of interferograms measured as we scan the delay, and here's the calibration measurement. We Fourier transform this to get the spectrum of the comb modes, and you can see that covers the astronomical H band and some of the astronomical J band here. And here's a plane Fabry-Perot echelon here with a piezo that you can just see, which is actuating the length of the cavity. Here are the individual comb modes resolved here. So we showed in earlier work presented here that we could annotate this these comb modes with an actual comb mode number, because there's enough stability here to plot these comb modes on a graph and figure out where that graph intercepts the zero frequency, and be able from there to infer the comb mode number. So one of the things that we had to do to achieve this was to improve the locking of the OPO. And the OPO itself is an unstable cavity. It has to be phase locked to the pulses from its pump laser. And normally that's done by monitoring the output from the OPO and scanning the length of the cavity and locking the length of the cavity, holding the length of the cavity always on a peak of the OPO transmission. So if we were to look at the output power of the OPO as we scan the cavity length, we'd see these peaks. And we want to operate around about here, at the peak of the maximum transmission, maximum output power. So normally this is done by introducing a piezo on one of the OPO mirrors and dithering it backwards and forwards to produce an error signal that looks like this, so that when you're on the peak, the error signal is 0. When you're on one side, the error signal is positive. On the other side, the error signal is negative. And that's used to drive the piezo either one way or the other. But this involves constantly modulating the OPO, which if you want a stable frequency comb is not a good thing to do. So we developed a new technique that made use of this green light here from the OPO, which is some frequency mixing light. And we observed that this green light, if we look at a portion of the green light by using a filter, there's a band of that green light which, as a function of OPO cavity length, has a function, shows a function like this, where at the point that the OPO gives maximum power, you're already on the edge of the green power from the OPO, meaning that you can do a side of fringe lock, because just at this point, if we move towards one side of the OPO peak, we'd have higher green power. We move to the other side of the OPO peak, we have lower green power. And so by setting a reference level around about here, we've made an error signal that we can use to constantly keep the OPO at the right cavity length. So we did that, and the details are probably a bit beyond what I want to speak of today, but we looked at, we measured spectra, we looked at the RMS noise and power fluctuations in the spectrum, locked with the traditional method, that's the dither locking, and locked with what we call the sum frequency mixing method. So we get lower power fluctuations and lower noise here. And we measured the noise using a power spectral density measurement called a RIN measurement, relative intensity noise measurement, that showed significantly smaller noise from the OPO when it was locked with this sum frequency mixing method. That's the red here, the red noise, as compared to locked with the traditional dither locking method. So there's a factor of about 6 or 7 improvement in the noise just by locking with this dither-free approach, and that's really helpful in allowing you to get a low noise frequency comb. So just as we conclude here, I know I'm almost out of time. I want to talk a little bit about some future sources that can be used in astrocombs. So clearly an astrocomb has to operate at a wide mode spacing, and one of the challenges is finding a laser that can start with a sufficiently wide mode spacing already, so that the amount of filtering required in a Fabry-Perot is kept to a minimum. So one approach is to use one of a generation of new lasers which can operate at multi-gigahertz rates. And so here's an example of an ytterbium ceramic laser running, developed actually by the group in Tokyo of Yohei Kobayashi. So we have rebuilt some of these lasers at Heriot-Watt. There's also a commercial 10 gigahertz Thai sapphire laser available, originally developed by Albrecht Bartels when he was at NIST in 2009. So we've used one of those 10 gigahertz Thai sapphire lasers as a pump source for a tiny OPO built by Richard McCracken and reported in 2018. Here's the OPO, here's a 1 pence coin. This is about 1 centimeter diameter, so it's tiny cavity, and you may just be able to see the crystal here. It's a Brewster cut PPKTP crystal, quite hard to see in these images. But here's the output of the OPO, running at 1.6 microns with a limited amount of output power. So one of the other things we've been doing is looking at more compact, more robust ways of building femtosecond lasers. So what you're looking at here is a 1.5 gigahertz diode pumped ytterbium ceramic laser that is bonded onto an aluminium breadboard using a proprietary technique that we've developed at Heriot-Watt in collaboration with the company Airbus. So I'm going to show you a video of this femtosecond laser running here, and I hope you can agree it's a very stable system indeed. So here's an optical spectrum analyzer. We've just turned off the power to the pump diode. It's now gone on again, and under this lid is the laser you can see on the left here. And now we're about to interrupt the beam with a screwdriver, so blocking and unblocking. And this laser now is self-starting, and it's running as a soliton laser at 1.5 gigahertz. So I think this demonstrates that this is now a very robust platform, either as being used as a kind of laser engine inside a more complex frequency comb, or as a standalone device for some application, maybe in a timing application. Okay, so let me conclude. So I've told you a bit about the use of and development of laser frequency combs based on sapphire lasers and how we've used them as a calibrator in the SALT telescope. I've told you about a method using Fourier-transform spectroscopy to analyze and understand the output produced by the astrocomb and look at that directly. And we've seen as well how these astrocombs are going to be necessary to enable some very challenging measurements performed by instruments such as high-res on the E-ELT telescope that will require comb coverage of several octaves from the UV to the near-infrared, and comb stability of at the level of 10 to the minus 10, 10 to the minus 11. So I think this is now my final slide. I just falls to acknowledge a number of my co-workers, both at Heriot-Watt University and collaborators at SALT, in Göttingen, Laser Quantum, Tokyo, Stanford, and the wider E-ELT calibration team. That's it. I'm hoping to be able to join to answer questions live, and all going well technically. I hope that's what I'm able to do now. But if not, you can always get in touch with me at Heriot-Watt University, and I'm happy to respond to any inquiries by email as well. So that's it. Thank you very much.
It's great to see you again. So, well, it's time to the questions. So let me read it because our set on YouTube. There is any questions from the audience, please? Oh, any questions? Can you hear me?
Hello. Yes, there's one question.
Okay, go ahead.
Are there Mexicans working at the E-ELT?
Okay, so the question was, are there Mexicans working at the E-ELT? My honest answer is I just don't know, I'm afraid. It's an international collaboration, of course, and you know, I would kind of hope that there would be some Mexican participation. It's being built in Chile, but I don't know, I'm afraid. So, the E-ELT has a really good website, and I would direct people to look at that if they want some information on the E-ELT.
Thank you very much. What's next for the project?
For the frequency comb project? Yeah, it's a really good question. So, as probably you saw from my talk, the overall architecture of the laser frequency comb has to be very complex. There have to be many parallel channels that are formed, each of which has a slightly different mode spacing, because as you go from an astrocomb in the blue through to an astrocomb into the infrared, the mode spacing has got to become closer together as you move to the infrared. And so that means really separating out each of these different channels through a number of individual Fabry-Perot ethlons. So we're at the point in the project where we're demonstrating two parallel channels, two different visible and infrared Fabry-Perots and the mode filtering that goes with that. But ultimately, this has to be done in parallel. The system has to be turned into something like a turnkey system, and it's got to be more reliable. It's got to be engineered. So we're in a kind of what would be called phase B, and ultimately this gets taken through to, I think, probably what used to be called phase D, which is a full kind of engineering build, a complete build. So we're at the point where now we're demonstrating the feasibility, and then once we've established that, it goes on to become commissioned as a full instrument. But the high-res instrument itself, the spectrograph, is not yet funded. It's not yet guaranteed for funding. So it's not going to be in the set of first instruments that go on the telescope. That will be things like the camera, obviously. But the spectrograph is in a kind of second tier of instruments. So it remains to be seen if there is, well, really what timescale that spectrograph, I think, happens on, and what the structure of the final collaboration is, and where the money comes from to put that together.
Thank you. Is there any application of microcavities for producing frequency comps for astronomical applications?
Really good question, and of course the answer is yes. I mean, there have been a couple of examples of using microresonators to produce astrocombs very successfully. The interesting comment might be that for many astrocombs, you want to operate with a mode spacing of around about 10 gigahertz. In the infrared, it becomes slightly less than 10 gigahertz for the optimum mode spacing. In the visible and blue, it becomes maybe 20, 30, even 40 gigahertz. So the microresonators are kind of good above 10 gigahertz. It's a bit easier to make things work, because below 10 gigahertz, you have to become really quite macroscopically big on the wafer. So there's kind of a sweet spot really for microresonators, which I think is above 10 gigahertz, but certainly they've been used and they've been developed for that. And it's absolutely a competitive technology. I wouldn't say it's necessarily a simpler technology, because there is a lot of infrastructure, at the moment at least, goes into making a fully phase stabilized microresonator comb as well. And the complexity is just different. It's in things like high precision CW lasers instead of mode locked lasers.
Thank you. What have the biggest challenges been for the project, for the COMP project?
So I think anyone who's worked with femtosecond lasers knows that they don't always work 100% of the time. And so I think for us, working with this is a Ti-Sapphire based comb system, and it's not based on a hands-free Ti-Sapphire system. It's one where it needs a degree of user maintenance. And for us, developing this over a number of years, and this has been a PhD project, and also was worked on before it was even a PhD project. So it's been going for maybe 5 years now. Our challenges are to keep the whole laser system running, because it's actually quite a complex chain of different sources and locked cavities, and so to keep all of that running at the same time is actually quite challenging at the moment. But we do hope to be able to make it more robust and rather simpler to operate in the future.
Thank you. What type of pulse compressor is used in the GHZ cavity?
In the which cavity?
Gigahertz or?
In the gigahertz cavity, yeah. So there's no pulse compressor in the gigahertz cavity. The gigahertz laser is actually a very simple design. It's a ring Ti-Sapphire laser, I think, with maybe 4 mirrors in the cavity plus the crystal. So the pulses that leave that laser are already effectively solitons that have been generated and shaped through a combination of the Kerr lens mode locking effect in the cavity and the cavity dispersion. So there's no pulse compression. These are intrinsically, these come out as maybe 30 femtosecond pulses directly from the cavity.
Thank you. Why is it important to use lasers for the frequency comps? I mean, it is possible to produce a comp from a frequency continuum, such as white light, and just filtering at appropriate frequencies?
Yeah, so that's actually there's a lot in that question. It's a good question. And I guess the person asking the question is really saying, well, why don't you just take a broadband incoherent white light source and put it through, you know, a Fabry-Pro echelon to imprint a mode structure? And the answer is that a Fabry-Pro echelon has chromatic dispersion. So its mode spacing changes with optical frequency or optical wavelength. And that means that the mode spacing is not, in fact, regular. The mode spacing starts to reflect variations in the dispersion of the mirrors, even in maybe the air that's inside the Fabry-Pro cavity. But the point with a frequency comb is because it's a mode lock laser, you fundamentally have this perfectly fixed set of pulses with a fixed interval in time coming from the laser, and that can be locked to a frequency reference, a timing reference. And so fundamentally, in the frequency domain, that corresponds to a rigid spacing of modes in frequency, which you can't get just by filtering a broadband source with in practice at least, you can't get by filtering a broadband source with a Fabry-Pro echelon. Now, in the E-ELT, of course, actually the primary calibrator will be, at least the proposal is that will be a filtered broadband incoherent source, which will suffer from this effect, that the modes produced by the echelon that thermal source goes through will not have a perfectly uniform spacing, but the frequency comb will be used to calibrate that, and so in a sense, ultimately, it's a comb that provides the absolute reference there.
Thank you. Are there further opportunities of collaboration available for Mexican researchers? If so, what's the procedure for the application?
Is this a question about Heriot-Watt University? I'll take it as meaning Heriot-Watt University. If it means the E-ELT, then that's probably quite a different question that I can't answer. But so Heriot-Watt University has a visiting scholar scheme, and what that means is that students or staff or PhD students can come over to Heriot-Watt University for a period of time. They can, if it's a long visit, then there might be a request for some bench fees. Shorter visits tend not to require the payment of bench fees, and they can be treated as purely academic collaborative visits. Yeah, these can happen kind of comfortably for up to 1 year, perhaps. And I mean, anything longer than that, probably, if it were a student, then it would be a case of registering perhaps that person as a student. But yeah, there are mechanisms for doing that. In terms of funding that sort of travel, I don't know of any grants that are uniquely UK Mexican at the moment, but you know, I guess one could look at Chromacity and see if there were any schemes that were available there. But I think you know better than I on what's available.
Thank you. Yes, well, the person who asked about the importance of lasers for the frequency comps, thank you for your explanation. And well, that's it. Thank you very much. Thank you very much, Professor.
You're very welcome.
Very well, thank you, Derryck. I would like to ask Derryck about, well, you already have some developments on tiny lasers.
Yeah.
At the end, you present a terbium-based mod-lock laser.
Yeah.
Yeah. So, but what about OPO? Because for a micro resonator, you will need a micro OPO. What about that?
So there was actually, I might have passed over it quite quickly in the talk, but in fact, I think one of the slides just before that ytterbium ceramic laser was in fact a micro OPO in a sense. It was a 10 gigahertz tie sapphire pumped OPO. So maybe you saw the one with the broadband spectrum at around about 1.6 microns with the 2 peaks. So that was a micro OPO, which is I think there's a photograph of it in the talk with a 1 pence coin, a penny coin. And yeah, that was pumped by a 10 gigahertz tie sapphire laser. So it's exactly what you said. It's a tiny laser pumping a tiny OPO. But I mean, as you can imagine, the alignment constraints are pretty severe in these geometries, and they do limit you as to maybe what flexibility you have to maybe optimize the alignment and get the best power out of the system.
Right, impressive, really impressive. All right, so well, we again would like to thank the talk, very interesting talk. Hope you can give us something else in the future, as always, Derryck. Yeah. And with this, we will end this session, and we would like to thank the presence and the attention from the audience, and see you in the next activities of the 50th anniversary of E-ELT.
Yes,
okay.
So happy birthday.
Oh, okay, thank you.
Right,
Thank
goodbye.
You, Derryck. Goodbye. Bye. Thank you very much.